Hello. Today I'll be going through the assignment, the MATT assignment that me and my partner did. So my partner is Yoke, I'm Samuela. So this is where we downloaded um our malware from. Here. One sec. Okay. So if you can download it here. Okay. So our file name is xclient.exe and I'll be going through our lab setup. We decided to use we have VMware installed and that's what we use to launch our virtual machines. And for our virtual machines we use Windows XP. It is what we are familiar with for in-class practicals, which um I used it for my basic static analysis. So these are the specs that we set up for the Windows XP that we use in class. And apart from the Windows XP, we also use Flare VM, which is an advanced reverse engineering virtual machine. It comes pre-installed with many malware analysis tools such as PEView, Detect-Easy, DNSpy, Procmon, Wireshark, RedShot. So um so before installing the Flare VM, the base VM is actually this specific Windows, at least for ours, because in order for Flare VM to be installed, you need Microsoft Defender to be off. Otherwise, there would be a lot of hiccups and Flare VM would not be allowed to install. So, but the thing is, most Windows out there, including Windows 10, that even if you turn off your um, group, even if you turn off your Microsoft Defender, even if you edited it in group policy to not turn on Microsoft Defender, if you do a reboot, your group policies and every setup for your Microsoft Defender will not persist. It will just turn back on like normal. That's why we needed one that has group policy edit persist even after reboot. That's why we chose this one. These are the specs that we set up the Windows 10 with. And then to install the Flare VM, we needed to first of all stop the Windows Defender. And then go to group policy. And then in group policy, you change this to enable. You enable this as well. You enable this. Then run the PowerShell as an administrator, and that's when you type this command in and it will load. So so in terms of what we did, how we split the work, I did the basic static analysis as well as the advanced dynamic analysis, whereas Yoke did the basic dynamic analysis and the advanced static analysis. But we do collaborate on certain parts so that one part isn't too overwhelming for one person to take care of. Okay, so we start with the basic static analysis, and we can see that this is the MD5 hash of the malware. And then you can open PEID. You can see that it is not a packed malware because in the EP section it says .txt and does not say any packer. Okay, so now I will be going on to here. So I've opened up the malware on Bintex. As you can see, it has some pretty interesting strings such as my web services, encryption AES, get web services, this. So you can see that there are some network-based indicators. There are also host-based indicators. Oh, there's monitoring. There are also host-based indicators. Now find them in dependency walker. So I've also opened up dependency walker over here and see that there are some few pretty interesting yeah, wow. Oh yes, pretty interesting ones like the SAM library. So as you can see that there are these functions, and when they call like SAM, this refers to SAM library, which is the library that contains all the Windows passwords, security access management. Yes, security account manager. So you can see that there are some few functions that I have noted out that I think um, tells a lot about the nature of the malware. So you have these. Yeah, and then so that is pretty much for basic static. A more in-depth one would be in the report. Okay, so we continue in the report. So you have another tool called exe info PE. So it helps to examine whether or not this the malware is obfuscated or is packed, compressed, or anything. So as you can see over here, since the EP section reflects the same as it did in PEID, it shows that the malware that we're using is not packed. However, you can see that over here, unpacked info obfuscated like DeepC, it shows that this malware is obfuscated. So we need to find a deobfuscator. Next, we went to VirusTotal, and then using the hash of the malware, we went to look it up on VirusTotal, and you can see that 55 out of 70 vendors had already flagged this as malicious. That means that this file is highly malicious and we should not just double click it like that. Yeah, you can also see the domains and IP addresses that it connects to. And then you have another tool, Detect It Easy. You can okay, so I can go here, and then this is where I already have a clean version of a deobfuscated version of the malware, which is this one. This is the unclean one. So I can open up Detect It Easy, and it can show the result. It shows that this this malware is anti-analysis, so it doesn't allow it to be run in a debugger or in a VM. Yeah.
Be talking about basic dynamic analysis. So basic dynamic analysis is the process of analyzing a program's behavior while it is running, usually in a controlled environment like a sandbox or virtual machine. So this is typically performed after basic static analysis has reached the dead end, where we have exhausted all the available static analysis techniques. So the tools I'll be using to conduct basic dynamic analysis are Apache DNS, Process Explorer, Process Monitor, and Ragshot. So firstly, Apache DNS is a tool used to control DNS responses through an easy-to-use GUI. So it is a phony DNS server that spoofs DNS responses to a user-specified address by listening on UDP port 53 on a local machine. So as you can see here in my virtual machine, after I've started the server, and this is the IP of my local machine, you can see the traffic that is redirected to my local machine. So I can see all the DNS responses here. Next, Process Explorer. It is an advanced system monitoring tool developed by Microsoft that allows you to view detailed information about running processes, such as which files and registry keys you have opened, as well as the DLLs that you have loaded. So this is a Process Explorer. So you can see all the processes that are currently running. and all like for example the description and the company name. Next is process monitor. So also known as Procmon, it is a real-time system monitoring tool that it is used to track various processes' activity in a Windows operating system. So this tool actually allows you to show how processes access files on disk, registry keys, and remote resources. So it actually combines the capabilities of two sysinternals utilities, FileMon and RedMon. So as you can see, process monitor. These are basically all the processes they are running as well. So this is the process name, and this is the operation, like what is happening, and this is the paths, and basically this is the results of the processes they are running. And you can see there are like details as well about the processes they are running. So lastly, we have Regshot. So Regshot is an open source utility designed to monitor and compare changes in the Windows registry. So it allows us to take snapshots of the registry at two different points in time and then compare these snapshots to identify any changes. So this is very useful for troubleshooting and monitoring system changes, such as software installations or modifications in system settings. So as you can see here, this is Regshot. So I can take the first shot. So this will be like the before like an operation or action that has taken place in this VM. So I can actually take a second shot as well, but this thing is not loading. But yeah, basically I can take a second shot and then compare in my first shot, and then I can see what changes have been made before and after. We're talking about advanced static analysis. So advanced static analysis is a process of deeply examining a file or program without executing it, going beyond basic checks like syntax errors or simple bugs to fully understand its behavior, structure, and intent, especially in the context of malware analysis or security research. So it typically involves disassembling, decompiling, and reverse engineering the binary code. So after doing basic analysis, we realized that the malware could not run on our XP virtual machine. So therefore, we decided to use the Flare virtual machine to carry out further analysis on our selected malware. So the tools I'll be using for advanced static analysis is D4Dot and IOSpy. So D4Dot is an open source deobfuscation tool designed specifically for analyzing and reversing obfuscated .NET applications. So we have actually used a tool called Detect It Easy during basic static analysis, and the tool actually showed us that our malware was obfuscated. So now I will have to use D4Dot to deobfuscate the executable file. So firstly, I open command prompt, and as you can see, the first command here navigates us to the location of D4Dot. So after going to the location of D4Dot, the second command runs D4Dot on the deobfuscated file, and this actually creates a new clean file in the same directory as the original executable. So as you can see here, D4Dot is cleaning our original executable, and after renaming all the obfuscated symbols, it is saving the cleaned version in the same directory as the original executable. So now we will have to open the clean file in IOSpy to read the deobfuscated source code. So IOSpy is an open source .NET assembly browser and decompiler that allows developers to examine and analyze .NET assemblies, decompile code, and modify compiled code. So as you can see here, I have done the analysis using IOSpy. I basically open the assembly highlighted in blue, which is our cleaned executable, and I control click the entry point, which is start main to navigate there. So after navigating there, we can see that there are many methods that were called. So there was a specific method that captured my attention. So the method is basically this run anti-analysis method. So this checks multiple anti-analysis functions like detect manufacturer, which checks if the system's BIOS or manufacturer string matches the VM. Then secondly, there's detect debugger, which actually looks for an attached debugger. Thirdly, there is detect sandboxy, which detects a sandbox environment. And the fourth one is XP, which checks if the OS is Windows XP. And lastly, there is AnyRun, which probably detects the AnyRun malware analysis sandbox. So if any of these checks return true, it will kill itself immediately. And also the environment fail fast is a .NET method that immediately terminates the process without running finally blocks, finalizers, or other cleanup code. So this actually prevents analysis from stepping through further code or dumping memory after detection. So this is actually a defensive code as it exists only to make analysis harder and avoid running in sandbox VM research setup.
Okay, so now we have the clean version of the malware open in a debugger. So okay, it's cleaned previously by Yoke using default.exe. So now it's no longer obfuscated, and you can see it in assembly. So as you can see over here, this is the disassembler, this is the registers, this is the stack, this is the memory dump. And the reason why we can open the malware in x64 debugger and not Olly debug is because I'm using the Skylar Hide plugin. And you can see over here, this is how I imported it. We're continuing so you can see. And I'm gonna open up plugins. You would see this, but that's because there's filter. So you should see these 4 files. When I set up, I only added 3 files, which is this DRL, the initializing the settings file, and this file. And this would allow Skylar Hide to be installed onto the x64 debugger. So the reason why you need Skylar Hide is because Skylar Hide will actually mask the presence of the debugger. It will intercept API calls that tries to find if there's any debugger present, and then it will reply no to it. That's why I can open the malware up here and not in I tried DNSpy. I could open it up in DNSpy, I cannot run the debugger in DNSpy. So these are the breakpoints that I set. Whenever I see the call, this is when I set it. You can see over here if I go to symbols, this is the DRL that it imports. But that's because it's not running, it's paused. So if I let it run, let's check back against the source. No DRLs. Maybe I'll just let it run here. Okay, so now this is based on what I did when I was testing them, when I was analyzing the malware. So see over here, you have this, it calls this function. Step over again. Now it calls this function. Wait, this one doesn't affect it. Yeah, it doesn't. Okay. Now I have this function. Checking again. Okay, so that function, the image thing, it does import a few modules. Let's take a look at the registers. So these are the functions that are called. You can see it's like loading library, this kind of stuff, right? Okay, let's go back. Load DLL. Anything? Nope. Set information to virtual memory. Oh yes, lots of things. Okay, so now we can track back which DLL is importing which function, which like which DLL is affecting what in the registers. Okay, so you have this clear DLL. You can see that it gets the file time, it gets the write watch, and then it connects to a pipe. It connects to pipe. So this DLL goes out. And then can look at more stuff. Oh wait, I saw it. Oh, maybe I saw it wrong. Maybe I go downwards. Get picture. Yeah, then you have the encryption of the API. It's here. Ooh, okay, so this is the DLL that connects to server WMI. And it does enumeration here. It does enumeration to find out more about target. Yeah, so this is a more in-depth demo would be in the report.
After completing our malware analysis, we have come to a conclusion that our malware is a XWorm v5.6.NET Remote Access Trojan, also known as a RAT, with a plugin system and a DDoS module. So how it executes is that it starts at the entry point start.main.main and runs an anti-analysis gate that terminates if it detects the debugger, VM, Sandboxy, Windows XP, or any run. It then decrypts its configurations using AES ECB with a key derived from the mutex via a 1-byte overlap copy to get important values like host and port. It then opens a TCP connection to the Windows Manager 53471.portmap.host on port 53471 and sends a system profile via info and begins the heartbeat timer. For persistent, it copies itself to app data, Windows Management Server.exe, and sets an HKCU run entry, a scheduled task, and a startup folder LNK. Finally, it enters a command loop that receives AES RED messages, splits them on the XWorm delimiter, and dispatches the corresponding actions. So for functionalities, some of the core functionalities is that the malware supports multiple execution paths, like FM, which performs fileless in-memory loading via assembly.load, and then DW that drops bytes to disk and executes, LN downloads to the temp and run shell executes arbitrary commands hidden. Then there's also a plugin framework that reflectively loads assemblies and invokes exported methods like run recovery, run options, UAC func, and ENC or DEC to extend capabilities on demand. For malware defenses, the malware implements layer evasion and operational security. So it performs a manufacturer of VM checks, debugger detection, and explicit sandboxy or any run and Windows XP checks, and will terminate immediately on any hit. So its configuration and traffic are also obfuscated with AES and compression, and the protocol uses a custom delimiter and marker. So for resilience, it supports self-update and can enable a critical process state to resist termination, which it later disables before exit or update. So for removal and containment, we can block outbound traffic to the Windows Manager on port 53471 and generally restrict unknown egress, and also terminate the malware process. So we can clean persistence by deleting the executable by removing the HKCU run value Windows Management Server and can delete the scheduled task via this command and remove the startup link at this directory.